Hello dear students, I am Pradeep Kotak here with you with the next topic of unit number 4, that is the speed control of induction motor. So in the last video we have seen the speed control of the DC motor. Here we will see speed control of the AC motor, that is particularly AC motor, induction motor. Okay. So different method by which the speed control of induction motor is achieved may be grouped under two main heading. So we can control the speed of induction motor by two methods. One is control from stator side and other is the control from rotor side. So there are three ways by which we can control the speed from stator side. One is the by changing the applied voltage, then by changing the number of stator poles, then third one is by changing the supply frequency, or it is also called as V by up control method. And from rotor side we can also control the speed, so by putting the rheostat in the rotor circuit. So the method is called as rotor rheostat control method. So first we will see control from stator side. So control from stator side. Okay, so number one, by changing the applied voltage. So by changing the value of the applied voltage we can control the speed. So how? See here, read this. This method, though the cheapest and easiest, but it is used very rarely. See, this is very cheapest method, as you all know that with the help of dimmer stat, or we can say it as with the help of auto transformer, we are starting our induction motor. As in your BDC practical, you have seen that we have started the induction motor with the help of dimmer stat. Okay, so that dimmer stat is nothing but the auto transformer. So with the help of that rotary switch we are changing the value of the applied voltage. So changing the value of applied voltage with the help of rotary switch is very easy. So that's why it is said here that this method is cheapest and easiest. Okay, there is no rocket science in this method, but it is very rarely used. It is very rarely used. Why it is rarely used? That we have to see. Okay, so large change in the voltage is required for relatively small change in the speed. We have to change the value of voltage in a large amount. Okay, so if the applied voltage is say for 15 volt, so if you are changing the value of applied voltage by 150 to 200 volt, then very minor change in the speed occur. So it is said here that large change in the applied voltage is required for relatively small change in the speed. So that is not beneficial for us. So what will happen if you are changing the applied voltage in large amount? Okay, this large change in the voltage will result in a large change in the flux density, because if you are changing the value of the voltage, okay, so it will affect the flux. So flux per unit area is the flux density. So ultimately it will affect the flux density, and if it affect the flux density, then the magnetic condition of the motor will disturb. Okay, thereby seriously disturbing the magnetic condition of the motor. Okay, that is not beneficial for us. Hence this method is rarely used, though it is simplest, cheapest and easiest, but it is rarely used. Okay, so this is the first method of stator side, that is the change in applied voltage. Now we will see a second one by changing the number of stator pole. Okay, all of you know the formula NS is equal to 120 F by P. Before this we have already studied this formula, where NS is the synchronous speed, F is the frequency and P is the number of pole. So from the above equation it is clear that the synchronous speed of induction motor could also be changed by changing the number of stator pole. Okay, so frequency F is fixed, frequency of AC supply is 50 Hz, so that will be constant. Okay, so by changing the value of P you can vary speed, synchronous speed. Okay, so that is written over here. From the above equation it is clear that the synchronous speed of induction motor could also be changed by changing the number of stator poles. Okay, this change of number of poles is achieved by having two or more entirely independent stator winding in the same slot. Okay, now after design we can't change the value of number of poles. Okay, if the machine is designed for 4 pole, then 4 pole remains constant. But if you have to change the number of poles, then what exactly you have to do? You have to design the winding in such a way that there are two slots it means that it can be achieved by having two or more entirely independent stator winding. So there are two independent stator winding. Okay, so you can change over from 2 pole to 4 pole, and so on in such a manner. Okay, so each winding gives different number of poles. So if one winding gives 2 pole, then other winding gives the 4 pole in like manner. Okay, and hence the different synchronous speed. If the number of pole goes on changing as the frequency is constant and number of pole changes, then your speed also goes on changing. So this is the second simplest method by which we can change the number of stator pole, and hence accordingly the speed of the induction motor. Okay, now a third one. This is the most important method from examination point of view. Okay, in most of the university examination paper, this question was asked. Okay, V by F control method of induction motor. So the name of the method is by changing the supply frequency, or V by F, V for voltage and F for frequency, V by F control method. Okay, the synchronous speed is given by Ns is equal to 120 F by P. Okay, you know this formula. Thus, by controlling the supply frequency smoothly, the synchronous speed can be controlled over a wide range. This gives smooth control of an induction motor. So by changing the value of frequency and maintaining the number of pole constant, you can also change the value of the speed. So how you can change the value of the frequency? This question will arise in your mind, that the frequency of AC supply will remain constant, but you can change it. Okay, so in power electronics there are various devices with the help of which you can change the value of the frequency. There is one device which is called as cycloconverter. So with the help of that cycloconverter, we are changing the value of your frequency also. Okay, so you can change. So if the value of frequency changes, it is obvious that speed will get changes. Okay, this gives the smooth speed control of induction motor. Okay, but the expression for the air gap flux is given by. Now the value of the air gap flux in induction motor, I told you this value. What is air gap flux? That is flux in between stator and rotor. There is a air gap in between stator and rotor, and the flux flowing from that gap is called as air gap flux. So expression for this air gap flux is 1 divided by 4.44 K1 TPH1 into V by F. Okay. So this is according to EMF equation of the transformer. So what is the value of EMF equation of transformer? I think this you have already studied in first year. Okay, if not, then remember this formula. Formula is V is equal to for EMF equation of transformer is V is equal to 4.44 F phi TPH. This is the formula. Okay, so from that formula we have written the value of phi. So here is the air gap flux, that phi is subscripted by G. So phi G is equal to 1 upon 4.44 K1 TPH1 multiplied by V by F, where K is the stator winding constant, TPH1 is the stator turn per phase, and V is the supply voltage, and F is the supply frequency. Now the name of the method is V by F control method. It is seen from this expression that if the supply frequency F is changed, the value of air gap flux also get affected. See here. If the value of this frequency F change, K and TPH1 is constant. The stator winding constant, TPH1 is stator turn per phase. That will remain constant. And if the value of, if you are changing the value of the frequency F, then your phi G got changes. Okay, means change in the frequency will affect the air gap flux. Okay, this may result in saturation of stator and rotor core. Such a saturation leads to sharp increase in the no load current of the motor. Okay, if you are changing continuously the value of the frequency, then your flux get affected. If the flux get affected, then magnetic condition of the motor get disturbed, and that leads to saturation of stator and rotor core. So what will happen if the saturation occurs in the stator and rotor cores? So that will leads to sharp increase in the value of the no load current. As you all know that no load current of the motor is very small, and if the no load current goes on increasing, then it will disturb the magnetic condition of the motor. Hence it is necessary to maintain the air gap flux constant when the supply frequency F is changed. It means that you have to maintain your air gap flux as a constant when you are changing this supply frequency. Okay, so supply frequency if you are changing, So with the help of this formula you can conclude that phi g will remains change, phi g will change, but you have to maintain this phi g constant. So how it is possible, we will see it now. Okay, to achieve this, it can be seen from the above expression that along with the f, v also must be changed so as to keep v by f ratio constant. It means that as you are changing the value of frequency and if you are changing the voltage v, it means that v by f ratio if maintain constant, then air gap flux will be constant, that will not be affected because k1 and tph1 is always constant. Okay, so along with frequency you have to change the value of voltage so that the ratio v by f remains same. Okay, that's why the method is called as a v by f control method. So how to change the value of voltage v along with the frequency, we'll see now. Okay, to achieve this, it can be seen from the above expression that along with f, v also must be changed so as to keep the v by f ratio constant. This ensures the constant air gap flux giving the speed control without affecting the performance of the motor. Okay, hence this method is called as v by f control method. Hence in this method, the supply to the induction motor is variable voltage, variable frequency supply and can be achieved by electronic scheme using converter and inverter circuit. This scheme shown in the figure below. So this is the most important diagram. So input is from this diagram we can conclude that how the voltage will change along with the frequency so that v by f ratio will remain constant. So AC is the input, constant voltage input. Okay, so that constant supply is given to the converter. Okay, converter convert this AC supply into DC supply. Okay, converter here, that is nothing but the rectifier. Okay, so that DC supply is given to the inverter. Now what is the function of inverter? Inverter convert DC supply into variable voltage, variable frequency AC supply. So after inverter, variable V, variable F AC supply, and that variable voltage, variable frequency AC supply is given to the stator of induction motor. It means that we can vary the frequency along with the voltage. Okay, so with the help of this circuit you can vary the voltage and frequency, and that variable voltage and variable frequency is given to the stator of the induction motor. Okay, so if variable frequency and variable voltage is given to stator of the induction motor, then your air gap flux, this air gap flux, see over here, this air gap flux phi g will remains constant. Okay, variable voltage, variable frequency means v by f, this v by f will remain same. Okay, so your air gap flux phi g will remain constant and magnetic condition of the motor will not be disturbed. So in this way we are maintaining v by f ratio constant. Okay, this is the description of the diagram. The normal supply available is constant voltage and constant frequency supply. It is given to the converter. Converter is a device which convert it to DC. This DC is then given to the inverter. The inverter is a device which convert DC supply into variable voltage, variable frequency is AC supply, which is required to keep the V by F ratio constant. So by selecting the proper frequency and maintaining V by F constant, smooth speed control of induction motor is possible. So in this way we are changing the value of the voltage along with the value of the frequency, and we will maintain the V by F ratio constant so that there is no change in the value of the air gap flux, and it will not disturb any magnetic condition of the motor, and in this way we can control the speed of the induction motor very smoothly with the help of this method, V by F control method. This is the most important question from examination point of view. Okay, so these are the methods from which we can control the speed of the induction motor from stator side. Remember this, control from stator side. Okay, so we have seen applied voltage control method by changing the number of stator pole and by changing the V by F control method. Okay, supply frequency. So now we'll see the control from rotor side. Okay, so this is different one. This we have seen. Okay, now control from the rotor side. Okay, so this method is applicable only for the slip ring induction motor. Okay, because in case of the squirrel cage induction motor, there is no terminal at the rotor side, as you all aware of that. Okay, so rotor rheostat control method. So here is rotor and here is stator. So you are applying three phase AC supply to the stator winding. Okay, and you are changing the value of the speed by inserting the rotor resistance in the rotor circuit with the help of this collector ring. Okay, so this practical we have already seen in the BDC. Okay, we have performed this practical. This is very simple. In this method, which is applicable to slip ring induction motor alone. Why it is said that slip ring induction motor alone? Because in case of the squirrel cage induction motor, there are no rotor terminal. Okay, it is short circuited. Hence, it is applicable only to the slip ring induction motor where the terminals of the rotors are out. Hence, we can connect the resistance to that terminal. Okay, the motor speed is reduced by introducing an external resistance in the rotor circuit. What will happen if you are inserting the resistance in the rotor circuit? The speed of the motor goes on decreasing. This method in fact similar to armature rheostat control method of DC shunt motor we have seen in the previous lecture. Okay, so it is obvious from this that the speed can be decreased by increasing the rotor resistance. So if you are increasing the value of the rotor resistance, your speed goes on decreasing. How? See, by increasing the rotor resistance R, as you are increasing the rotor resistance I square R, this is I square R. Okay, I square R losses increases. If the losses increases, what will happen? Operating efficiency decreases, which decreases the operating efficiency of the motor, and if the efficiency decreases, then your speed also decreases. So in fact, the loss is directly proportional to the reduction in the speed. It means that this if I square R loss goes on increasing, then your speed goes on decreasing. Okay, so this is the topic, that is control from rotor side with the help of rotor rheostat control method. So here we have finished all the important topics of unit number 4. So in next video we will see some new topic. Okay, thank you very much for watching this video. Bye bye for now.